Okay, so we mentioned that this is a linear program. Okay, this is a linear programming formulation. Of course, we also know that sometimes we hope the solution, the flow size, are integers. Okay, maybe you are shipping air conditioners. Okay, you are shipping laptops. You hope your solution are integers. We also understand that this may not always be required. Even if you are talking about concrete units, you may still use a linear program to approximate. And if you get fractional solution, you still are able to do some rounding, whatever. So integer variables should be seriously used only when, first, your approximation by rounding is too inaccurate and should not be allowed. Okay, in that case, you really need to talk about integer variables. Or second, when you are having binary variables, using them to model those if-else for if-else either or, select at least two, at most two, or fixed charge. When you use binary variables, then typically they should not be replaced by fractional values. Okay, so suppose we are having these two situations, then sometimes we hope we may have integer solutions for free. So the interesting thing for MCNF is that, well, we get integer solutions for free. What does that mean? As long as your supply quantities and the upper bounds are all integers, then a solution for the LP would just be an integer solution. Okay, so your Uij and your Bi should all be integers. When that happens, then you have integer solutions. Or say it in another way, suppose you have an IP formulation. Okay, you set those Xij to be integers. Then if you solve the LP relaxation, you solve your IP because your LP relaxation must give you an integer solution. So this is a special property, right? In the past, you have solved all kinds of linear programs. Typically, your coefficients are all integers, but you don't get integer solutions. Somehow, you get fractional solutions, typically. So this must because the problem is special. And for the formulation, this means the coefficient is special. Let's see what's that. So to understand that, we need to first introduce this idea called total unimodularity or totally unimodular matrices. So what's the definition? The definition is that a square matrix is called unimodular if its determinant is either 1 or -1. Okay, cannot be 2, cannot be 1.5. Its determinant must be 1 or -1. So that allows us to define a totally unimodular matrix. A matrix is totally unimodular, or sometimes we abbreviate it as BTU. This guy is totally unimodular if all its square submatrices are either singular or unimodular. Unimodular means the determinant is 1 or -1. Singular means the determinant is 0, right? So somehow that means if you give me a matrix, for example, this matrix A, if you give me a matrix and then I can choose any way to get a square submatrix. If that's the case, and whenever I choose one, I would see its determinant either 0, 1, or -1. If that's true for all square submatrices, then this matrix is totally unimodular. Okay, so let's see two examples. For example, A, if you choose your submatrix to be 1 times 1, so for each number here, you must satisfy this unimodular constraint. So in this case, you understand that if a matrix can be totally unimodular, all its elements must be either 1 or 0 or -1. So that's the first criteria. And then, for example, if you pick a matrix here, well, its determinant is -1, right? If you pick another one, for example, here it's -1. If you pick another one like this, okay, so very quickly you may calculate that its determinant is 0, 0, 0, okay, minus 0, minus 0, minus 0. So this determinant is 0. So you may try to see all the possible square submatrices are either singular or unimodular. So for B, this is not true. Okay, so we may see that, for example, if you consider the whole matrix B, okay, then you will see that its determinant is 0 plus 0 plus 0 minus 1 minus 0 minus 1. So the determinant of B is actually negative 2. Okay, this violates the requirement of unimodularity. So B is not totally unimodular. So there must be a reason to talk about totally unimodular matrix. The reason is here. Because total unimodularity gives us integer solutions. So let me read this proposition. Consider a standard form linear program. We want to minimize C transpose X subject to AX must equals to B, X is non-negative. Okay. So for a standard form linear program, if your coefficient matrix A is totally unimodular, and if your B are all integers, then for any optimal basic feasible solution, you must have it satisfies the fact that all the values must be integers. Okay, so somehow this idea applies to basic feasible solutions. Optimal basic feasible solutions, those things obtained by the simplex method. Okay, so let's see why it is true. So whenever we are solving a linear program with the simplex method, always we have basis and the set of non-basic variables. Okay, so actually even if you don't use the simplex method, eventually your solution pretty much are extreme point solutions. Okay, corner points. So still you may separate them into basic, non-basic. Okay, so if you have that, then your solution X may be split to XB and XN, and your XB would be AB inverse B, which is the values for your basic solutions, basic variables. So all we need to do is to convince you that AB inverse B indeed are all integers. And this comes from a fact from linear algebra. So whenever you have a matrix A or matrix AB, okay, so AB, as you know, is a square matrix. Its inverse may be determined in this formula. Well, you first find its determinant, put it as the denominator. And then for the numerator, it should be a square matrix, right? So in the numerator, this is the adjugate matrix for AB. Okay, so what's that? Okay, so let's say AB has 9 values. All right. So how about AB inverse? For AB inverse, each element, for example, AB 1, 2, AB 1, 2 would be the determinant of the matrix obtained by removing row J and the column I from AB. What does that mean? So for AB, if this is talking about 1, 2, then I'm going to eliminate row 2 and the column 1. Row 2 and the column 1. And then for the remaining 4 values, they form another square matrix. I'm going to calculate its determinant and put it here. Alright? So that's how we say, how we define the adjugate matrix for AB. Oh well, so you feel tired because these things all look so weird. But the proof is almost complete. Why is that? Because pretty much all we need to do is to use the following argument. If A is totally unimodular, okay, A is the original matrix, okay, AX equals B, A is the original coefficient matrix. If A is totally unimodular, then whatever basis B you choose, okay, whatever basis B you choose, you know its determinant must be either 1 or negative 1. So first, it cannot be 0 because if it's singular, then that does not form a basis. Okay, so it must be 1 or -1. If that's the case, then whatever thing you obtain here, its denominator is 1 or -1. So you are not going to get fractional value due to this division. Okay, and then lastly, all the numbers here are also integers. So then we guarantee your xb would be an integer vector as long as the given b is also integer and a is totally unimodular. All right? So I would say this seems to be weird if this is the first time for you to see it. But to understand this is not too difficult. The definition of totally unimodular was there. And for simplex method, you know there is a basis, there is a set of non-basic variables, and you also know something about this linear algebra thing, or at least you trust me. And if all these things are connected, then you are able to prove this. So the implications for IP is here. If we have a standard form linear program that has a totally unimodular coefficient matrix, an optimal basic feasible solution would always be integer. Or we are talking about IP, then its linear relaxation always gives us an integer solution. The branch and bound tree would be finished by just solving one node. So that means whenever you have a problem where your coefficient matrix is totally unimodular, then you may feel free to set the variables to be integers. That does not create any complexity to your problem. The problem may still be solved very easily. Okay? So in general, this helps us to tackle an integer program in a different way. When you have an integer program, it would be difficult to solve it, and you may be hesitate to use a branch and bound to solve it. But actually, if you understand that the coefficient matrix is totally unimodular, then actually branch and bound becomes an efficient, good algorithm because we have done the analysis. We know its coefficient is totally unimodular, and then using the branch and bound is good enough. There's no reason to consider other algorithms. All right? So this is again another example showing us that good algorithms for solving a problem starts from a good analysis.